So here is the rest of the lesson on Chapter 7 with the ionic bonds and ionic compounds. What we learned in class was the first of 4 main points, which was that although they're composed of ions, ionic compounds are electrically neutral. So when we choose a metal from the left side of the periodic table and a non-metal from the right, that is ionic bonding, and we end up with ionic compounds. So it took this guy's positive charge with this guy's negative charge to hold them together, but once they're together, they really are neutral. Of course, we can pull them apart again and make them charged back into ions, but we're not ready for that yet. So here are the other 3 points that are important. Most ionic compounds are crystalline solids at room temperature. Hey, guess what? Sodium chloride, crystalline solid. That's the picture on the lower left. And here is grossolarite with calcium, aluminum, and silicon tetroxide as these pinky crystals in here. So these molecules are able to form crystals because they make layers and layers and layers, one upon the other, in the same repeating pattern. So when you know that each ion is attracted strongly to each of its neighbors, the repulsions are minimized, and you can make these nice big crystals in just the right conditions. So main point number 3, ionic compounds generally have high melting points. So you're looking at all of these things in crystal form, and I want you to imagine a piece of ice. These crystals that you're seeing are the same thing as ice. If we get these hot enough, they would melt, which is kind of a weird thing to think. But you know that you can melt rocks. We call it lava. Actually, we should only call it lava if it's coming out of the Earth's crust. If it's inside the Earth still, we would call it magma. Okay, so we can get these crystals hot enough to melt them and turn them into magma. Just like you get ice hot enough, which isn't very hot in our estimation, but you can get ice to turn into a liquid. We call it water. So very high melting points for these types of ionic compound crystals. So would we expect to find the sodium chloride in underground rock deposits as a solid, a liquid, or a gas? Right, as a solid, because we know that sodium chloride is an ionic compound and it has a very high melting point, which means what temperature did we need to go from solid to liquid? And we're talking thousands of degrees Fahrenheit or Celsius. So this would be a couple thousand Fahrenheit, 800 Celsius. So now, here's this other concept that the book is introducing, which I will explain why we need to use this in class. But just for now, you need to know simply the definition, that there's a thing called a coordination number for an ion when we put it into a crystal. And the coordination number of an ion is simply the population of opposite charges that surround that charge in a crystal. So each ion in sodium chloride has a coordination number of 6. Why? Because if you look at the chlorine right here in the center and you count, I should have used a different one. Skip that one. Look at the sodium in the center. How many different negatively charged chlorines did we need? Well, here's 1, here's 2, 3, 4, 5, 6. And so this sodium that was in the center is connected to 6 chlorines. Now, are you sitting there saying, but wait, Mrs. Mitchell, that sodium is only a single positive charge? Why does it have 6 negative charges? charges around it. And then you zoom out from that single sodium and you realize that it's like a network. You have this chlorine, which is attached to that sodium. So if we say this is where those two electrons are getting ripped off and assigned, then I can match up another two, if I do it right, of where these electrons are actually getting shared. But the beauty is, and we really know, that these electrons, they don't really care which other atom they go to. They just need to either leave from the sodium or sort of stick around the chlorine. Other molecules have different coordination numbers. In cesium chloride, each ion has a coordination number of 8. So it's like sitting in the center of a cube, and it has a connection to each of these 4 vertices on top and 4 vertices down below. Now, if I switch and make this chlorine the center of this diagram, I will have the exact same thing. I will have this in the center of a cube with vertices made up of cesium, positive cesium ions. Here's another one. Titanium dioxide, we sometimes call it rutile, forms tetragonal crystals. Now, you got to think back to some geometry. We'll study this crystallography in a little more depth. But do you see basically that there's a rectangle here? And since I'm highlighting it in yellow, you should be imagining a stick of butter. So here's the stick of butter. Now, what are the corners made of? The corners are made of little titaniums. 1, 2, 3, 4. 1, 2, 3, 4. Then, for those titaniums, we're going to count how many positively charged O2 oxygen ions are around each one. So, if I look at the one in the center, if I look at the titanium in the center, it's connected to 6 other oxygens. And if instead of looking at this particular titanium, if I looked at this one and drew the rest of the diagram out over here, it too would be connected to 6 oxygens. This is the first one, and you don't see any of the others. So, when you look at the opposite ion in titanium dioxide, it has a different coordination number. So now, if I'm considering the oxygen ions, that coordination number is 3. Simply meaning, let's get out a different, let's clear that whole slide. There we go. So now, if I start looking at, we can use this one. This oxygen ion right here is connected to 1, 2, 3 titaniums and nothing else. It wouldn't be connected to another oxygen because the oxygens all have negative charges. We care about how many connections it's making to positively charged things. So I'll explain why coordination numbers are informative when we get to class. Now, your fourth idea. Ionic compounds can conduct electric current when melted or dissolved in water. How often have you melted salt? Right, never. How often have you dissolved salt or have experienced dissolved salt in water? Yeah, all the time, especially when you go to the beach. So we dissolve sodium chloride all the time. That's no problem. Sometimes when you get into big industry and the solar collecting industry, you'll start to melt sodium chloride. So you take a big pot full of little sodium crystals, sodium chloride, salt crystals, and put some heat under there, and voila, ta-da, we've got liquid sodium chloride. So that comes in handy when we're trying to do some very special things with conducting electric current and have a very high temperature to do so to keep everything or dissolved in water. And you're thinking, well, what wouldn't conduct electricity if we melt it or dissolve it in water? One sort of outlier example would be oil. Oil is not an ionic compound. It's a carbon compound, but it doesn't have this ability to trade electrons and kick one electron out and sort of Newton's cradle. You hold one side and the ball hits all these others and another electron pops out at the other end. So oil would be something that doesn't conduct electricity well because it doesn't have any of these free electrons. So here is a picture of melting sodium chloride, because we break down this nice sort of cube structure that we end up with. Oh look, and there's a picture of a solar panel, solar collector. So now, when can ionic compounds conduct an electric current? Is it when they're melted? When they're melted or dissolved? Only when they're dissolved? Or when they're solid and melted? Good, you're paying attention. B, when they're melted or dissolved. And so, recap. Here are the 4 things that you need to know about the ionic compounds. This one we covered in class. This video covered these last 3. There are some definitions that might come in handy